Okay, so we've now covered all of the convergence tests that we're going to look at for the quarter. And so if you look at question 9, this question is really about strategizing which test to use when. Okay, it says use an appropriate convergence test to determine whether the series converges or diverges. And before we jump into these, I want to point your attention to the following document. Okay, this is called Convergence Tests / Strategies, and I've posted a copy of this under the Week 2 module on Canvas. And on the front page, this is just a summary of all the highlights from these last few sections. So you see geometric series, harmonic series, p-series, the integral test, ratio test, alternating series, and the alternating series estimation theorem. Okay, now on the back side, this is what I want to focus on in this video. This is where I discuss different strategies for applying the convergence tests. Okay, and so first thing to check, which is usually pretty easy to check, is whether or not the series satisfies the divergence test. Okay, so remember that if the nth term a sub n does not approach 0 as n approaches infinity, then we're done, right? In that case, the series is divergent. Okay, now if it is the case that a sub n approaches 0, then the series may or may not converge, right? That's where we need to try something else. In other words, use another convergence test. Okay, now is the series geometric? This is also usually very easy to determine, right? Is there a common ratio for the series as you move from term to term? If it is geometric, then we can easily tell whether it converges or not, because remember, a geometric series will converge when the common ratio r is strictly less than 1 in absolute value, and otherwise it diverges. Okay, and if it does converge, okay, furthermore, we can compute its sum using first term divided by 1 minus common ratio. Okay, another thing that's easy to spot, are you looking at a p-series? In other words, is your series of the form where you're summing 1 over n raised to the p power? Okay, if you are working with a p-series, you can determine its convergence and divergence, recall, by the following result. It converges when the exponent p is strictly greater than 1, and it will diverge when the exponent p is less than or equal to 1. Okay, so that's pretty straightforward. Now, moving on, is the summand a sub n easily integrable? Okay, something like a sub n, which is equal to n times e to the negative n squared, right? The antiderivative here is very easy to find just using a substitution. And is a sub n positive and decreasing, right? If these two conditions are satisfied and the integral is relatively easy to compute, then you might want to consider using the integral test. Okay, now what if the summand is, say, made up of things like products, factorials, which really is a type of product, or exponential functions, stuff like 2 to the n? Okay, in that instance, the ratio test might be the way to go. And the reason why is that when you take ratios of products, factorials, exponential functions, these types of things, you get a whole bunch of cancellation, which is really nice. Okay, so you might want to consider using the ratio test. And then lastly, does the series alternate, like the series right here? If so, you may want to consider the alternating series test. All right, so now with all that in mind, let's go ahead and jump into part A. We're looking at the sum of negative 1 to the n times n squared plus 2n minus 7 all over n squared plus 8. And here n starts at 1. And so here's our a sub n. Does this thing go to 0? Well, the answer here is no. Okay, the negative 1 to the n, that's just going to alternate sign. And this expression approaches 1 as n approaches infinity, and that's just because we have a quadratic function in the numerator and denominator, right? Note if I divide numerator and denominator by n squared, we get this expression, which we can easily see approaches 1 as n approaches infinity. So that says a sub n, for n really large, right, will take on values really close to 1, and then negative 1, and then 1, and the negative 1 is going to alternate, right, between values like that. So in particular, what we really care about here is the fact that a sub n is not approaching 0. And so we conclude that this series diverges by the test for divergence. All right, moving on to B. looking at the sum of 1 over n times the natural log of n cubed, and n starts here at 2. Okay, now here, that's a relatively easy integral to compute. You can use the substitution. And if I let f of x be 1 over x times log x cubed, okay, this function is non-negative and it is decreasing on this interval from 2 to infinity, and so the integral test does apply. So let's compute that integral. Okay, I'm going to use the substitution u is equal to the log of x, so du is dx over x. Change the limits of integration, so when x is 2, u is the natural log of 2, and as x approaches infinity, u, which is equal to the natural log of x, that also approaches infinity. Now in the denominator, the natural log of x cubed will just become u cubed, and dx over x, which is right here, is just du. Okay, now integrating 1 over u cubed, that gives you negative 1 over 2u squared. And now we want to go ahead and evaluate, and for this limit here at infinity, right, this expression goes to 0, and so we get a finite value for this improper integral. So in other words, this integral converges, and since this integral converges, the integral test implies that this series also converges. All right, not too bad. Let's go ahead and check out part C next. So here, we're looking at the sum of negative 1 to the n times 2 to the n over n plus 2 factorial, and n starts at 1 here. And as we noted on that document, right, I have factorials here. I also have this exponential expression, so ratio test might be a good way to go. So here, a sub n is negative 1 to the n times 2 to the n over n plus 2 factorial, and so a sub n plus 1 is negative 1 to the n plus 1 times 2 to the n plus 1 all over, and then I'm just replacing n with n plus 1 down here, and that simplifies to n plus 3 factorial. Okay, so now to compute this ratio of a sub n plus 1 and a sub n in absolute value, I'm going to go ahead, like we've been doing, take a sub n plus 1 in green here, and then I'm going to multiply it by the reciprocal of a sub n. And now let's go ahead and simplify. Okay, the 2 to the n plus 1 over 2 to the n, that's just a 2. The n plus 2 factorial over n plus 3 factorial, I simplified that over here. So for the numerator, that's just the product from 1 up to n plus 2. And for the denominator, we're going to get that same product up to n plus 2, but then we get this one additional factor of n plus 3. So dividing out, this all simplifies to 1 over n plus 3. And also note, I do have these negative 1 to the n plus 1 and the negative 1 to the n, and that'll simplify to just negative 1, but I'm taking the absolute value. So I've gone ahead and just ditched the absolute value, and that removes the negative. All right, so now we can go ahead and compute our value for r, which is the limiting value of this expression, and we see that's equal to 0, and since r is less than 1, the ratio test implies that this series converges. All right, moving on then to D. We're looking at the sum of 1 over n raised to the 1 point and then 0, 0, 0, 0, 1. And n starts here at 1. Okay, well, this is a p series, right? It's a p series with exponent p, which is equal to 1.00001. And so in particular, since p is greater than 1, this is a convergent p series. All right, and then for the very last part, I'm going to make some space here. We're looking at part E, and you see that this is a alternating series, and so we could apply the alternating series test with b sub n, which is equal to 1 over the square root of n. And, well, the sequence 1 over the square root of n is clearly decreasing, and so the first condition is satisfied. And b sub n, which is 1 over root n, clearly goes to 0 as n approaches infinity, so that's also satisfied. And so we conclude by the alternating series test, this series converges. All right, well, that is going to do it. Thanks so much.